In this video, we're going to discuss some of the periodic trends. We have looked previously at SP, D, and F, and I hope that has allowed you to revision why the periodic table might be oriented the way it is. Here are some more trends that are very nicely go along with our periodic table. And so I'm hoping by the end of this video, you'll be like, oh man, that periodic table, that's some pretty neat stuff right there, because you can learn so much just by looking at it and generalizing from its location on the chart. So for instance, ionization energy is the first trend we're going to look at. Ionization energy is the energy required to remove an electron from an atom in the gaseous state. What in the world do I mean by this? Well, let's look at lithium. Lithium is over there on the left-hand side of the periodic table. It's in the group 1A, which means it has one electron in its outer valence shell. So if that's the case, how hard is it to remove an electron? Not very. Why? Because it wants to form Li+, it wants to lose an electron. And so its ionization energy is relatively low, okay? Whereas if you compare that with fluorine over there on the right-hand side, fluorine has a very high ionization energy. Why? It has 7 electrons in its valence shell. Since it has 7, it really wants to have 8. So how much energy is it going to take in order to remove an extra electron from it? A ton, because fluorine is not going to give up any of its electrons without a fight. So it has a really good or really high ionization energy. If you want to think about it as this way, it's the fighting energy. How much of a fight is it going to give up in order to form an ion or a cation? Okay, so fluorine does not want to become a cation under no circumstances. So it's got a very high fighting energy or a very high ionization energy that's going to require a large amount of energy in order to remove that electron from the atom. And then just by definition, it's always in the gaseous state. All right, so I kind of put these little charges on here just to remind you. These are the charges the atoms normally form. The francinium there in the bottom left-hand corner is the element with the lowest ionization energy. Okay, so that makes sense as why when you go from left to right, the ionization energy increases, because we can see that fluorine would be a lot harder to remove an electron than lithium. But why going down does it get harder to remove an electron? Because lithium, it's got a lot higher ionization energy than francinium. Why is that? Okay, well, what's the difference? Lithium is smaller than francinium. So as you increase the principal quantum number, you're increasing the distance that electron is, which is negatively charged, remember, from the positive nucleus. And remember, electrons are attracted to things that are positive. So if we are separating in space that electron from the nucleus, the positive pull on that electron is going to be a whole lot smaller. And there are also a whole bunch more electrons in between that electron and the nucleus. This is something called shielding. So therefore, it's going to take less energy to pull that electron off. It's already barely feeling the positive pull of that nucleus. And so you can pull it off more easily. So that's why as you go down within that same group, going from lithium to francinium, it is going to be very easy to pull off an electron. So your ionization energy is going to decrease because you're not going to resist that very often. Okay, and then this other statement that you see at the bottom, it gets harder to remove an electron as the outer shell becomes more full. That's just generalizing the trend from lithium going all the way over to fluorine. The outer shell of fluorine is more full than the outer shell of oxygen. Therefore, fluorine has a higher ionization energy than oxygen. So here's my general trend. So I just make little post-it notes like this, and I write down the definition of the word, and then I make a note that if this is the periodic table that you see represented by the square, it's largest up here in the top right and it's smallest in the bottom left. And if you can kind of explain why the trend is the way it is, that is the big importance as far as conceptualizing this goes. All right, so here is a chart that's describing the trend. So notice going from lithium all the way up to neon. Neon has the highest ionization energy, and this is something called first ionization energy. The first ionization energy means pulling off 1 electron. The second ionization energy is what happens when you pull off 2 or the second electron from it. And so notice neon's the highest, but there are some exceptions like beryllium versus boron. Boron's is slightly lower. And it's just a general trend. As you go from left to right, it gets higher. But are there exceptions? Absolutely. But can you generally know it by looking at its location on the periodic table? Absolutely. All right, so here are all the first ionization energies, and they are listed. And so you can kind of see that the depth or the height is supposed to be the highest. And so here you can see neon is actually slightly lower than helium. What about second and third ionization energies? Well, look at this chart to see. Sodium versus magnesium. So notice where sodium and magnesium are. Sodium's in the first row, so it's going to want to give up an electron pretty easily. But once it does that, it's now going to have 8 electrons in its outer shell. So it's going to be pretty stable. So how do you think the second ionization energy is going to be compared to the first? It's going to take a whole lot more energy to remove that second electron, and that's where you see the break. So sodium, its second ionization energy is huge because it wants to give up 1 electron to become Na+. There is no reason sodium should ever be Na2+. And the reason for it is the energy barrier that would have to be overcome is so high that this just does not happen. And so your second ionization energy is huge for sodium. What about for magnesium? Why is the second ionization energy not just as big of a drastic jump? It's because magnesium wants to form 2+. So its first ionization energy is low, the second ionization energy is a little higher, but then that third ionization energy, the amount of energy that it would take to remove a third electron from magnesium is huge because that would form magnesium 3+, which we know does not occur. And so looking at these trends, you can see that it's slowly increasing the amount of energy it needs to remove every single electron. And then there's a huge jump, and that huge jump happens after it has a fully stable octet or stable 8 electrons in its outer shell. And so that last jump is always the hardest. Okay, and so kind of think through this and think about what this means as far as trends. If I were to ask you, hey, aluminum, which of its ionization energies is the largest? Do you know if it's 1, 2, 3, or 4? Just by thinking that aluminum needs to be 3+, therefore to remove the 4th electron is the tricky part? You should. The next trend we're going to look at is electron affinity. This idea is what happens when you add an electron. Instead of taking one away as in the last trend, what happens when you add it? And so typically with fluorine, if you add an electron to it, that's going to be pretty probable. That's going to happen. And so when you add an electron to fluorine, it's going to become more stable. Therefore, it is going to release energy to form that more stable energy configuration. Okay, now something to think about here is the more negative something is, the more energy that's released. Whereas going all the way to the very bottom, it's still going to be a negative energy change or a release of energy, but it's just less of that energy is released. So it's more positive. It's not that it's positive, it's more positive. So the idea here is which elements have the greatest electron affinity? Those that are generally at the top right-hand corner. All right, so what about atomic size? Where are our biggest elements located? They are located at the bottom left, which makes sense. As you go down a group, you expect them to get bigger because you're increasing your principal quantum number. So meaning going from hydrogen down to cesium, cesium is definitely bigger than hydrogen. It has more electrons, and so you're increasing your number of your principal quantum numbers. So for cesium, you're going to have some electrons in 6s. And so you're going to have a very large atomic orbital, and that's going to be a lot bigger than the little electrons that are in the 1s orbital for hydrogen, and so you're going to have a bigger atom. But why, if you will, does it decrease going from left to right? So going from 1a to 8a, why is cesium bigger than radon? Well, if you think about it, it's because you're still adding in extra electrons to the same subshells, so your 2s, so cesium and barium, see how they're kind of close? You're adding an extra electron into that same 6s orbital. But you're increasing the number of protons. So your size of your orbital shouldn't get any bigger. It's the same energy, but you're adding in more of these positive entities into the center. So what's going to happen? It's going to pull it closer. So the ring is still 6s, but your ring just got pulled in because you have more positive forces pulling it in. Same thing going all the way across. So with radon, you now have a whole bunch more protons. It's going to pull in that 6p subshell. All right, so here's just another, my words, just kind of explaining it as to why that happens. As you increase number of protons in the nucleus, you pull the electrons in closer to the nucleus. And we're going to think about how this applies to such things as sodium and potassium in a little bit. All right, atomic size. So the general trend for this is it's bigger in the bottom left and it's smaller in the top right. Okay, so here are the different atomic radiuses that you see. Cesium, barium, all of them, okay? But notice how it's biggest in the bottom left and going to the top right. Now, all of these sizes are in picometers. Picometers is 10 to the negative 12. So that means that like hydrogen is 37 picometers or 0.037 nanometers. Just stop for a minute and think about how the atomic radius changes. It goes from hydrogen to cesium, it gets a lot bigger. Hydrogen to helium, it gets a little smaller. So this is a good just summary slide, kind of comparing the big three trends we looked at in this video. So ionization, electron affinity, and atomic size. You should really kind of know what they all are and then know the kind of direction from big to small that they trend toward.